So indeed, this is a continuation of the workshop that we had in Toronto, and there has been lots and lots of more interest in these kind of problems in recent years, and certainly also from the point of view of condensed matter physics, there has been a lot of progress made in understanding somehow the impact and somehow the need for looking at marginals, and this has brought lots of new insights into description of quantum many-body systems. And I would like to give a sketch. So what I will talk about is not very advanced in the sense that it's not really it's not very technical. I would rather like to give you some kind of an overview of why is it so natural to look at marginals when you want to study quantum many-body systems or kind of quantum spin systems. So and actually the marginals that we will look at are kind of a little bit different than the ones that we have seen in previous talks on fermions. So because the setting that we will be interested in is actually something like a chain. So you have a spin chain. That means like you have all spins. Of course, this is an abstraction of some kind of a much more complicated kind of system. It could be that you have like a chain of ions, and then around these ions you have some kind of electrons that are kind of orbiting. But you make abstraction of that, and you say, okay, actually my degrees of freedom, I can describe them by some kind of a Hilbert space that is d-dimensional, and I have n of those kind of d-dimensional particles. Okay, these are your spins. This could be 2. And you have n of them, so you can, of course, the Hilbert space is a tensor product space. And typically, we work in something like second quantization, or what means is that any vector in that Hilbert space is actually a valid physical vector. So we don't have to kind of anti-symmetrize or these kind of things. This is already kind of included in that formalism. If you talk about spin or spin systems, this is just a vector space. We have a vector space endowed with the tensor product structure, and we're interested in basically kind of getting the features of these vectors. So again, there's no anti-symmetrization. All these kind of things are not needed. This is kind of already included in the way we kind of set up the problem. Okay, and what happens is that, like in one-dimensional spin chain, this typically we are interested in the case where this is infinitely long. Okay, this actually simplifies things when you consider systems that has some extra symmetry, namely translational symmetry. Okay, that means that if you kind of shift the system, shift all these kind of the system by one side, you get exactly again the same the same system. And what the central object in condensed matter physics, especially the condensed matter physics of strongly correlated systems, is to identify kind of ground states and of local Hamiltonians, and then kind of investigate what happens if you change some parameters in these Hamiltonians. You can kind of have quantum phase transitions. You can have kind of there's all kind of rich phenomena that can occur. So what is a typical Hamiltonian looking like? It's something like let me write down the Heisenberg model. Okay, so this is minus. You label your site by I. Okay, so this is, and let's say that this is sigma x on site I, sigma x on. So let's assume that somehow we have spin 1/2. Okay, so we have a system of, so every kind of local kind of quantity is described by spin 1/2, and somehow these are the Pauli matrices acting on somehow the ith spin. So what you have is typically like this: sigma y, I plus 1, and for kind of reference later I will put the delta here, sigma z, sigma z, I plus 1.
Do you have a preferred direction?
No, this is actually completely invariant under under reflection. Okay, but what we have here is a Hamiltonian that basically tells you that the only interactions, the only terms that you're interested in are kind of the terms that connect two sides next to each other. Okay, because somehow the higher order terms, the Hamiltonian terms that kind of connect particles further away from each other, they kind of are much weaker. So you can kind of ignore those. Okay, so what you're interested in is like in finding eigenstates and especially ground states of Hamiltonians of that kind. So you could ask, why is it that in physics people are always talking about ground states and all these kind of things? It's actually because this is like an effective model describing all these electronic degrees of freedom that are going on there. And for electronic systems, somehow the typical let's say, typical energy scales. Okay, so because you have to kind of the Pauli exclusion, where you have to fill your kind of shells and all these kind of things. This is on top of that, but somehow this means that the typical energy scales are like, if you kind of would phrase it in terms of temperature, are like in the order of 10,000 Kelvin. Okay, that means that room temperature for electronic systems is extremely cold. Okay, because somehow the typical kind of energy scale for these kind of electrons that are on top of your Fermi sea are kind of 10,000 Kelvin, but nevertheless our room temperature is extremely cold. And that's why actually what we are interested in, what the physics that we see kind of does, is we are interested in kind of the very, very low energy physics of that. We want to find what are the ground states. And what does an energy mean? An energy is somehow this, you see this is an operator. This is actually a Hermitian operator, okay, because it's...
Could you say what sigma I x means?
Oh, these are the Pauli matrices, okay, so sigma x...
What's the difference between x and y?
Maybe write them down.
Sigma x is 0, 1, 1, 0. But if I write sigma xi, that's actually a shorthand notation for this is what happens on this ith kind of Hilbert space, tensor the identity on everything else.
Yeah.
That's actually what we mean. So you have an identity operator everywhere except here where you act with that kind of operator. That's sigma x. Sigma y is equal to 0 minus I 0.
Quick turn, yeah. Okay.
And then sigma z is equal to 1, 0, 0, minus 1.
What's this thing that looks like Laplacian?
This is a sum, is that the thing?
The delta.
Triangle.
Oh, delta, but this is a free parameter. Okay, so actually this is because I will need it later in the talk. So in some sense, in many ways, what these two terms kind of describe is the kinetic energy. So these two terms kind of describe something like the kinetic energy, the fact that kind of electrons can hop from side to side. And this kind of term is responsible for interactions between electrons, okay, because they are kind of diagonal, but somehow this is the physics, but this is a parameter, okay, just a free parameter that depends somehow on the microscopic details of your model. Okay, so what we will be interested in is indeed kind of ground states of that model as a function of delta. Okay, we'd like to see what happens if you vary this delta. How do the marginals change? How do the how does everything change as a function of this parameter?
Quick question. What was that 10,000 degrees argument? What were you saying?
And this is just to argue that actually this is why we are interested in ground states. That somehow.
Where did that number come from? I've heard you say it before. I never.
So if you fill so if you have fermions, let's assume that they are not interacting. Okay, that you have free fermions. You have to fill somehow your Fermi sea. And typically, somehow, at the top of your Fermi sea, somehow, if you look at the energy of these things, this corresponds to something like if you would have one electron at 10,000 Kelvin.
But this is without the exclusion principle.
But this is included there, because that's why you have to fill your Fermi sea. So the exclusion principle is exactly what kind of makes that for electrons somehow their energy is very, very high. But anyway, this is a kind of don't take these kind of arguments to see it, but it's to argue somehow why is it that we are interested in ground states in low energy states.
It's just that I thought this was the case when you had drew the model, and then Beta Sommerfeld came, included the exclusion principle, and temperature was not 10,000 anymore. But maybe that's a different thing.
Well, let's talk about that later. That's really has nothing to do with the rest of the talk. So let's talk about it later. Okay, so we see that this Hamiltonian has indeed lots of symmetries. Okay, in the sense that it is, for example, completely invariant under translation. So if I kind of take the translation operator t. Okay, what is t doing? It's kind of basically taking a wave function. Let's assume that it's on a ring. Okay, so that somehow that spin can be identified with that one. And if I kind of shift my kind of Hamiltonian by one side, okay, and that this is the shift operator. It shifts the whole thing. You can see that t times h that t minus 1 is equal to h. Okay, this is exactly a symmetry that these Hamiltonians have. Okay, that means that actually your eigenstates of your Hamiltonian, all the eigenstates, because somehow these are low energy states, and of course low energy states, because of the variational principle, these are like the lowest energy state is an eigenstate of this. They can be labeled by momentum. Okay, they can be labeled by the eigenstate of the shift operator, and the eigenstates of the shift operator are exactly kind of the eigenvalues of the shift operator are actually complex numbers. Okay, e to the ik, and this is what we call momentum. So if people talk about momentum in physics, it's actually nothing more than actually an eigenvalue of the shift operator. Okay, and if you have a finite kind of system, then these kind of k, these values k, they must be of the order 2 pi divided by n times some kind of a number I. Okay, and that's okay because you need somehow these are, well, if you have to do it on a ring, but of course if you kind of go to the thermodynamic limit, and that's the limit that you're interested in, then this can become any number. Okay, that's any number between 0 and 2 pi. Okay, so it's even true that, of course, that the extremal eigenvalues, extremal eigenvectors of any Hamiltonian actually has the maximal symmetry possible, and actually it means that actually that there is guaranteed to be a ground state that would be also translation invariant. Okay, so it means that if somehow you look at the extremal eigenvectors of this H, there's guaranteed to be at least one ground state, namely the one with the least energy, such that this T times psi 0 would be equal to psi 0. Okay, that means that indeed somehow these states that we're interested, they are translation invariant. They have a symmetry, namely if you shift that state with one side, you get again the same state. And actually this is the key somehow. This will, you will see that this is actually a very, this puts lots and lots of constraints on what the marginals of that state can be. Okay, because somehow you have a many body wave function. Okay, this is just defined in this humongous Hilbert space. But somehow we're interested in many in kind of wave functions that have some symmetry built in. Namely, if you shift them, you get the same state. And this is a very non-trivial kind of symmetry to how to parameterize states with that property is actually not an obvious thing. Okay, and that's one of the main kind of topics that will arise later. But what is more important, if we kind of can restrict ourselves to states that have this symmetry, then the energy of that kind of state will solely depend on just one simple reduced density matrix. Okay, because if somehow your state is translation invariant, you calculate the expectation value of your kind of Hamiltonian with that thing. Okay, so of course somehow because this is a sum over I with this, somehow because it's translation invariant, this is nothing more than actually the expectation value of one term, namely h I plus 1, I call it, psi times n, with n the total number of sides that you have. If you have n kind of sides here, then this somehow the expectation value would just be equal to the expectation value of psi h I plus 1 psi times n, okay, because it's translation invariant. And this, of course, you have to kind of, let me get a little bit more precise. This is this tensor, the identity and all the rest, psi times n. Okay, but this, somehow in quantum information theory, we actually, so what is clear is that this is equal to rho I plus 1 times h. So again, somehow I have to apologize. This whole kind of, my whole talk will be very, very simple. Okay, there's no advanced mathematics or anything that will kind of come, but I kind of want to convey a little bit the message of somehow why marginals are important. So I have to apologize for the simplicity, but somehow I still think it's important kind of message that I want to give. Well, it doesn't matter. I'm not consistent at all, so it doesn't matter. It's an operator.
T is translation, I guess.
Yes.
Hat is.
Well, it's an operator. I put a hat when it's an operator, and if I don't put a hat, yeah. So, yeah, we are in quantum mechanics. We don't care about this. It's always clear what it means.
Frank, I have a question. Is on the definition of the translation invariant? It's like exactly same to the sort of up to the phase, or sort of without. It's the included in the phase.
So you're guaranteed that the ground state actually has phase 0, okay? Because of because it's an extremal eigenvector of your Hamiltonian, and then it has actually the same symmetry as your eigen.
It's like any state is just a no translation symmetry. That's just for only the ground state.
No. What I said is there's guaranteed to be at least one ground state that has the symmetry. Okay, there could be other ground states that don't have the symmetry. Like if you would have like a staggered magnetization, spin up, down, well, then there's also kind of down, up, and then you can take the superposition of these two, and the superposition of these two would exactly have this symmetry.
Yeah, but that could still be a phase. That's what you said.
Yeah.
The energy.
Yeah, but the only thing I was saying, there's at least one ground state that has this property, and that's what I kind of will care about.
Yeah, but thermodynamics could
be. Yeah, phase could be exponential of I theta.
Well,
yeah.
So what? Sorry, what was your comment?
But when delta is not 1,
Yes.
then thermodynamically we know that there are other ground states.
Yeah, sure, but again, I was only saying there's at least one, okay, and I'm interested in this thing, okay, I'm interested in the translation invariant ones. That's what I want to say. That's the guy we will be interested in.
What is the E?
If that's the
E?
I think it's not
The last part you wrote.
Rho. Okay, so let me explain. Indeed, so what you have here is that you have a you have a non-trivial. Let me explain this more carefully. So you have a Hamiltonian acting on this kind of I and I plus 1. So this is side I. This is side I plus 1. But you kind of trace out, so you don't care about all the rest. There's an identity operator on all the rest. So how do you define? So that's why in that sense somehow the reduced density matrices that I will talk about here are kind of different than the reduced density matrices that people use in quantum chemistry. Okay, so this reduced density matrix, well, it's different because it's like, so the reduced density matrix means that you trace out actually all these kind of particles. So what does it mean? So yes, this state, you can write down the wave function for the many body state. Okay, and that wave function we can basically reshape it. We can so this is just a huge vector. And what we can do now is kind of write this vector in a matrix form, where this kind of thing, if this would be qubits, would be somehow the indices somehow related to these two kind of Hilbert, to somehow the tensor product of these two Hilbert spaces. Look, in the case of qubits, this would be a 4-dimensional Hilbert space, and this would be a 2 to the n minus 2-dimensional Hilbert space. So I'm just kind of rewriting my state as a matrix. Okay, so we just kind of reshape your vector and like this. Well, what this rho would be, let's call this matrix, let's call it x. Then this rho is actually nothing more than x times x dagger. Okay, that's actually what we mean by a reduced density matrix, because somehow what you see is that you act with the identity everywhere. So that means that actually the action of calculating that quantity, you can first basically calculate the reduced density matrix. You can take the partial trace, that's what we call a partial trace, just kind of introduce an identity operator and kind of contract all these indices somehow with respect to this thing. And what you leave open are actually these indices. And then somehow you get an operator that is positive, okay, because it's kind of a partial trace of some kind of an operator, and then you kind of multiply with your Hamiltonian term h.
Basically, you're doing the same thing as in the unrepresentability, but you're replacing the anti-symmetry condition by a trace invariance condition.
Exactly.
And this X operator is what you get if, that's when you take a reduced density matrix and you do this, what people call the Schmidt expansion. If you simply did it in product states, you would.
Exactly.
You get that's what the.
So this is what we call somehow the reduced density matrix. Okay, and this you see that. So this is actually very much related to
factor of n to the
well times yes. So this is very much related to the talk that the very nice talk that Maribeth gave. Namely, means that at the end we want to kind of, you see that the energy is solely dependent on somehow this reduced density matrix that acts on this very tiny kind of dimensional Hilbert space. In this particular case, it would be like a 4x4 matrix. Okay, because if you have kind of spin 1/2, means that somehow you restrict yourself to translation invariant states, then somehow the only thing that you want to kind of are interested in is what are the conditions on this kind of reduced density matrix of this 4x4 block. That's the only thing that you have to know to basically identify or to be able to kind of know what the ground state energy is, or somehow this is all the information, what the magnetization would be in that state. So it's all kind of encoded in that very simple kind of reduced density matrix. Okay, so let's try to kind of, so what we are interested in is, of course, this is not just an arbitrary reduced density matrix. It has to be a reduced density matrix from a state that is translation invariant. Okay, and that's exactly kind of the competition that you will have. Okay, so it's very easy to kind of to say what kind of what are the kind of conditions for a density matrix to be positive. Well, it just has to be a positive operator. Okay, you can say actually what are the conditions on a density matrix? It has to be positive, and the trace has to be equal to 1. Okay, and then, but of course somehow what is very clear, and that's actually that's why entanglement will play a very important role in these kind of things. That somehow there are certainly states that satisfy this that cannot be the reduced density matrices of a translation invariant state. So let's, for example, assume that, let's take an example, let's take rho to be the singlet state. Okay, S and the singlet is equal to somehow, well, let me write it down in quantum language, 101 minus 10 divided by square root of 2. Okay, so we have kind of a Hilbert space with a tensor product. Okay, and this is like this is the first qubit, the first spin 1/2, the second spin 1/2. And this is a singlet state, Okay, and this is actually what is maximally entangled. And what happens is that somehow, if your reduced density matrix would be this, it would actually kind of, if you kind of would forget about this delta, this exactly that state would minimize the energy with respect to that Hamiltonian. Okay, so that's the first guess. Then I say, well, what will be the energy? What will be the kind of the minimal energy? Because this is actually an eigenvector of this local Hamiltonian. So this is the eigenvector of that local Hamiltonian with the lowest with the lowest energy. But somehow that means that if you kind of have this would mean that you have a singlet between these two sides. But of course, it has to be translation invariant. So you also want to have a singlet between these two sides, and you want to have a singlet between these two sides, basically. And this is exactly where some property that's called the monogamy of entanglement kind of comes in. And somehow I think this property of monogamy, and maybe I think Barbara was the first one to kind of claim that name, no?
I think it was Bennett who had was talking about it, and then.
But you wrote the paper
I
on
put
it.
it in a paper because in honor of Bennett, yeah.
Exactly. So what happens is that there's some notion of monogamy of entanglement. So if I have a particle, if I have this spin 1/2 here, okay, I have this spin 1/2 that is maximally entangled with the one sitting next to it, then actually it cannot have any entanglement with anything else. Okay, that's why somehow the more entangled you are with somebody, the less entangled you can be with somebody else, and that's why Barbara kind of phrased the term monogamy. That well, doesn't really mean that it's monogamous. No, it can still be entangled with two, but less. Okay, and that's at the heart actually of trying to understand somehow the features of this convex set. There's this kind of competition between kind of trying to make the correlations as large as possible. So this is why is this state somehow a good state, because it has the maximal local correlation. It kind of minimizes the local energy, but it violates somehow the fact that it comes from a translation invariant state. And it's really this competition between symmetry, namely translation invariance, and extremal local properties that kind of drive that kind of are responsible for all the properties of ground states. Okay, and you will see somehow that these two things are of course not compatible. Okay, extremal local properties versus kind of lots of symmetry, and this is this competition that we will try to kind of understand better. Okay, so for this, let's try to kind of look back at this model. Why do we look at this model? Because this model is actually integrable. So what does it mean to be integrable? You can solve it. It means that actually the ground states of that model and the ground state energy can be found exactly by something that is called the Bethe-ansatz. Okay, so there's a humongous literature on these kind of exact solutions for these models. It's not trivial, but somehow this is a very nice kind of mathematics involved in this. But it means that somehow actually we know the ground state energies of this model. Okay, so let's try to kind of see how the ground states look like. Actually, there's much more symmetry in that state than just a translational, in this Hamiltonian than just a translational Hamiltonian. Okay, so for example, because the term here for the XX and the YY term. So how does this Hamiltonian look like? It actually looks like something like wait, I have to kind of see X. So there's a 1 here, a 1 there, a 1, a delta, minus delta, minus delta, delta. So this is the kind of local Hamiltonian written in somehow the basis of two nearest neighbor qubits. Okay, and that's why somehow you immediately see that indeed somehow the lowest energy will be obtained by basically acting with that singlet on that space. That's what will give you the lowest local energy. But you see that there's lots of more symmetry. There's lots of symmetry in that kind of thing. Namely, you can, for example, do an arbitrary kind of rotation on these coordinates, because this 2x2 block, okay, is kind of well, it's basically the identity up to this. This is the identity here in this large 2x2 block. So you can do an arbitrary rotation in that space. There's lots of symmetries in that Hamiltonian. And actually, because ground states are always somehow there's at least one ground state that actually inherits all the symmetries of your Hamiltonian. Then this implies that actually the reduced density matrix for the ground that the reduced density matrix for one of the ground states will actually have exactly the symmetry. So that means that you will be able to parameterize that reduced density matrix as something like 1/4 times the identity, tensor identity, plus let's call a small x times sigma x tensor sigma x, plus sigma y tensor sigma y, plus a z times sigma z tensor sigma z. Okay, so this is just, so because of the symmetry somehow you just can believe, I think you can believe me that indeed, so there will exist a ground state that actually has all the same symmetries at that thing. Okay, that means that there's actually two parameters that parameterize the reduced density matrix for the ground state of that model. Okay, so let's try to plot how somehow this reduced density, how this convex set looks like as a function of these two parameters x and z. Okay, so again, somehow I'm just giving an example, but this example kind of contains the main ideas of why reduced density matrices are also kind of interesting. So let's kind of, and as you will see, there's actually lots and lots of information you will be able to get out by just making pictures like that. Okay, so let's try to understand how this convex set looks like. So the first thing we want is, of course, that this is a positive operator. Okay, so what it means is that, so the conditions that this is positive, I have to kind of C is actually, so the conditions that this is a positive operator, they look like this. Wait, I have to, if this is, this would be 0. So this is when x, this is the x-axis, this is the z-axis. So here, z is equal to 1. Here it's minus 1. This is also minus 1. And this is plus 1. So just requiring that this reduced density matrix is a positive operator makes that somehow these parameters x and z must lie within that kind of very simple polytope, okay, namely this triangle. So all positive states lie in this thing. But that singlet, for example, that I was talking to you about, would exactly correspond to this point. So it's clear that this cannot be part of the convex set of reduced density matrices of translation invariant states. Okay, so this point must be excluded. And the question is, how does that kind of shape look like? And because we know all the ground state energies as a function of delta, okay, so as Maribeth explained us, actually, that's what does that mean if you know the ground state energies of that Hamiltonian as a function of delta? It is like somehow the trace of h of delta times any rho that's dependent on x and z. Somehow what does the ground state kind of correspond to? The ground states will of course correspond to somehow, will have reduced density matrices that are extreme points of this convex set with respect to somehow this Hamiltonian. And this Hamiltonian we see is just linear in this delta. So that means that actually what this induces are kind of hyperplanes. So you say, I fix a delta. What it does is actually saying, well, I fix a delta. This is like saying, how far can I push somehow this kind of, so this delta will kind of define an angle, because of course within this picture we know exactly how the energy depends. So given x and z, we can immediately kind of calculate the energy. Namely, it's just 2 times x plus delta times z. So the energy as a function of delta is minus 2 times x plus delta times z. That's the energy for a state, because this is the trace of rho times h. Okay, this is this energy as a function of delta. But we know this is given basically that formula by the beta ansatz. Okay, that means that this is actually the dual problem, and this kind of defines all kind of hyperplanes. Okay, it tells you if I kind of have a certain angle delta, somehow this is the distance that I can push this kind of hyperplane away from my zero, such that it will just touch my my convex set that I'm interested in. Yes.
Do you really want the minus sign up in the Hamiltonian?
Yes.
Then it's the fair, and that's trivial. And then delta. You want the parameter.
Yeah, I want the maybe I don't want the minus sign. Indeed, you're right. Well, yeah, probably you're right. This is I don't want minus. Well, it shifts it just, I think the only thing that happens is you have to.
No, because then delta is independent of delta.
Sorry.
Then E of delta would be independent of delta.
Yeah, sure. So I want the antiferromagnetic.
Oh,
For sure. I want the antiferromagnetic.
Or it would be just delta.
Yes, indeed. This is the energy as a function of delta for these reduced density matrices. Okay, and this is so, and you can make this plot. Okay, so you can actually you can see somehow if I define a certain delta, how far can I push this, and you make this plot, and what you see is that actually what comes out. Let me take a different color. What comes out is that all the states somehow they look like this, and then this is symmetric. Okay. It happens that the convex set that we're interested in is exactly the convex set inside this kind of of tier, or this kind of this blue kind of curve. So this happens to be the convex set that characterizes somehow all possible reduced density matrices of translation invariant states. Okay, at the end, of course, this is a statement independent of the Hamiltonian. This is just saying I take a state that is translation invariant, look at somehow it must have some symmetries, and look at the reduced density matrix. Well, this reduced density matrix, with if you kind of look at x and z, somehow this x and z parameters must lie within this kind of nice kind of convex set. Okay, so now let's see what. So how do you draw this? Is of course by kind of looking at the dual problem and kind of drawing all these kind of curves. Now we know that exactly this E of delta. So this kind of defines somehow lines in this. So you have for every delta you have a formula like this. Okay, so for every delta somehow it means that you have a line that you can draw somehow, and you have the let's say the convex hull of all these lines is exactly that convex set. Or the convex hull is that, well, whatever. You understand what I mean, no? So every Hamilton. So it means that actually the ground state for a Hamiltonian with a certain delta will exactly correspond somehow. The reduced density matrix will exactly correspond to an extreme point of that convex set. That means that the extreme points of that convex set are a one-to-one correspondence with the ground states of your Hamiltonian. Okay, so that means if you're interested in ground states, you should only kind of care about these extreme points of this set. So you can play the same game now, not in one dimension, but in two dimensions. Okay, you could ask, what happens if somehow I have more conditions? That my Hamiltonian is not just kind of connecting these particles, but I also have kind of other particles underneath it. So I have kind of particles here. Okay, and actually so this also goes on from minus infinity to plus infinity in this direction. So and your Hamiltonian is the same. So it just not only has terms that act on these two spins, but also has terms that act on those two spins. Okay, and of course, if this Hamiltonian is again kind of invariant under kind of rotations and all this kind of thing, it means that actually there will be a ground state that it has much more symmetry than that. Not just this symmetry, but also will independent under rotations over 90 degrees. It will also kind of be translation invariant in that direction. And again, you can ask the question: how do the reduced density matrices look like? Because now you have more conditions. This reduced density matrix, this one is not only equal anymore to that one and equal to that one and so further. It also has to be equal to that one and that one. So you have much more conditions. So this convex set will shrink. Okay, so and the question is, how will it shrink? What you see if you do this, that this line is completely equivalent, but somehow it looks like this. Okay, so you see that somehow instead of this outer line, somehow there's less conditions. Okay, so and that has to do with the fact, of course, that and indeed the entanglement that I have now in my system has to be shared not just by my left and right neighbor, but also with my neighbor up and down. This has exactly to do with this monogamy kind of properties that Barbara found. And you keep on increasing the dimension. Okay, you go to 3 dimensions, 4 dimensions, and so further. And what you see is that actually this convex set will converge to a nice kind of diamond, a very simple kind of line. Okay, so but maybe I'm going too fast. Let's again. So you have all these kind of hyperplanes, and what you see is that actually when you come here, somehow this is a face of your. So these are faces of your convex set. So here it's nice kind of curved, but here it's a face. Okay, so what happens is actually that this is exactly the ferromagnetic case. Okay, so if you somehow from the moment this delta is large enough, you're in the ferromagnetic case, and you see it doesn't matter anymore. Somehow, if I increase my angle of that hyperplane, somehow I just will always kind of end up in that point, and that's exactly the case that you were mentioning. This is like the ferromagnetic case, because somehow it doesn't matter what the angle is. Somehow it will always touch here. Okay, and then suddenly somehow if you keep on increasing that angle, suddenly somehow you will jump to that case, and then you increase it a little bit more, and you will suddenly jump from there to there. Okay, that will be the reduced density matrix of the ground state. And actually what these things are first order phase transitions. Okay, it's really somehow you have something that happens, and then suddenly you change some parameter in the Hamiltonian, and you ask, what is my kind of extreme point that's just kind of on which, such that I can push that line as far as I can from 0, such that it exactly touches, and you see somehow if this, you keep on increasing this, suddenly you jump here, and then somehow you continuously kind of go here. So here it's a nice smooth curve, and then Somehow this, so this shows you that actually there's lots of information that you can get out of this picture. Okay, so for example, ferromagnetism would kind of be this whole region. This is kind of, and you also see that this whole region survives if we kind of go to 3 dimensions, 4 dimensions, to infinite dimensions. You could ask, what is this kind of diamond that I get here in the middle? It happens that these are exactly the states that are separable. Okay, these are exactly the states that have no entanglements whatsoever. So all the states in that kind of diamond are separable states. And what is, okay, because I kind of think I have to mention this briefly to, because there's probably a few people in the audience that have not, that don't know the definition of separability. What is a separable state? A separable state means that actually our state can be written as a convex combination of product states. Rho tensor. Well, so we have a state defined on tensor product of 2 Hilbert spaces, and rho I b. Now, a state is separable if and only if you can write it as a convex combination of tensor products of positive operators. Okay, that's actually what, if a state is of that form, we claim that there's no entanglement in the state. Okay, and why is that? It's because somehow from the operational point of view in the quantum information theory means that actually these states you can create locally. You don't need somehow to, so there's never kind of, you never need interactions between A and B to create these states. Okay, somehow, so there cannot be entanglement. Somehow there has never been an interaction between the systems in A and B, and therefore there cannot be entanglement. That's, there's many kind of reasons why to introduce this. I will not kind of try to justify this definition, but that's what we call separability. And it happens that Reinhard Werner, long time ago, I think in the end of the 80s, he showed that a state is separable if and only if it's infinitely times extendable. So it means that a state is separable if and only if somehow there exists somehow a larger state, namely a rho A, B, let's call it C1, C2, Cn, such that somehow all the marginals of A and B is equal to the marginal of A, and C1 is equal to the marginal of A and C2, and so further. So this state kind of has, is complete. So this is exactly the properties that indeed we have here if we kind of go to infinite dimensions, because I want the reduced density matrix of this guy to be equal to the reduced density matrix of this guy, equal to the 1 in 3 dimensions, equal to the 4, and somehow this fits exactly this definition of kind of extendability. And therefore somehow the state must be separable, and that's exactly given by this.
Sorry, why cannot you put one C with high dimensions?
Sorry?
One can you not you put one C, not NC, but one C with high dimensions?
But that's not allowed. So there are entangled states such that actually this is the thing. It must be infinitely times extendable.
What means it infinitely times?
Well, there must.
Do you require them to be qubits? This C.
No. Well, no.
Then if C is arbitrarily large, what does it mean?
No. So what I'm saying is, I have a state rho AB.
Yeah.
Then there must actually exist a density matrix defined on more than these 2 sites, namely on C1, C2, C3, and infinitely many different kind of copies of that same Hilbert space, such that all the marginals are equal to each other. Namely, the marginal of AB of that bigger state is equal to the marginal of AC is equal to the marginal of AD, and so further. But you need infinitely many kind of you have infinitely many conditions actually. No, well.
I think he wonders about the purification, or
you can just take one big system C.
But the condition would have to refer to the subsystem.
but then the purification doesn't satisfy the symmetry.
States are obtained from an infinite tree. How do you obtain this? If you put your system on an infinite homogeneous.
These results that I show here are for infinite systems, yes. It just happens that this is, well, we can do it for that particular model because it's integrable. There's lots of hidden symmetries, and that's why somehow you can actually do that exactly for that model, and that's why you can kind of come up with this exactly. Now, other things that you can discover actually is that in that purple curve here, actually, there is an extra phase. You can see, you can plot this. You can just do some numerics and plot this, and suddenly somehow what you see is that there is actually a phase in the middle of that thing. Okay, it's curved, and then there's a phase, and then again it's curved. So that means that actually these kind of things exactly kind of show that in that model there's kind of a first order phase transition going on. Okay, namely, somehow what happens if there's a phase you kind of turn your Hamiltonian, you change your parameter, and suddenly somehow you kind of get in that phase, and then you can change your parameter, and you stay there, and then you jump. Okay, so it means that suddenly, somehow from the moment you kind of jump, that means that a tiny change in the parameter of your Hamiltonian has a huge impact on the reduced density matrix, because you will jump from this kind of reduced density matrix to that one by kind of an infinitesimal change in your Hamiltonian. So that means that actually by looking at pictures like this, you can basically discover the whole phase diagram. You can see kind of all the information about how the reduced density matrices look like, what the magnetization is, what somehow, whether it's a first order phase transition that is going on. You can all see this from this picture. There's even more. Somehow you could ask the question, what happens, for example, for what kind of Hamiltonian is the ground state mostly entangled, so has the largest amount of entanglement? Okay, so this is the kind of another question that you can ask. And this is now, in that particular case, it's very easy, because somehow, if you would measure the amount of entanglement as being somehow the difference between the energy, if you allow for any state that is translation invariant, or if you kind of limit yourself to separable states. Okay, so it would basically be the distance between somehow that separable cone and somehow the true kind of convex set. And it's obvious from this picture that this distance will be maximized, because it's a convex set, will be maximized exactly for the Heisenberg model. Okay, because for the Heisenberg model, you're exactly kind of hitting, you have a line that is parallel to that convex set of separable states. So it immediately shows that actually the Heisenberg model is the one that is mostly entangled, has the largest amount of entanglement. So you can all see this kind of, so you can see all these kind of features by looking at these reduced density matrices.
Frank, sorry, just one question. So when you build up this set, or the blue set of states,
yes,
you did it by imposing that the energy of the reduced two-body system has to be equal to the beta ansatz value. Yeah.
This just gives me curves. And gives me hyperplanes.
What does what guarantees that this state will be a marginal of the many-body quantum system? That I don't understand. So you know only that
because I know that there is a ground state that has all the symmetries, namely translation invariance, and actually also has all the symmetries. There is at least a ground state that has all these symmetries. Therefore, this kind of finding ground state of that thing implies that there exists a state that has this kind of marginal, a ground state.
Maybe that there are more states that have that property.
No, sure. That's I'm not claiming that this is unique. Okay, so the question whether somehow there's only one state with that marginal is indeed equivalent to asking, is the ground state somehow, is there a unique ground state of Hamiltonian or not? And this is actually very much related to the question that Marie-Beth kind of raised in her talk, somehow, that there are indeed somehow, it is clear that actually you can have some degeneracies of ground state that you cannot see somehow locally. Okay, and that's kind of, these are exactly the states that have topological order and things like that. This topological order are exactly the states that Marie-Beth was talking about. So indeed somehow, by looking at this, you cannot make claims about the degeneracy. Okay. What you could do though is make these convex sets and kind of plot them as a function of the size. Instead of kind of working with an infinite system, you could kind of start plotting them as a function of n. Okay, with n the number of sides, you have a ring, and you kind of plot how does this convex set kind of shrink if I kind of make n larger, or kind of grow somehow. So how does this convex set kind of change as a function of the number of spins I have? And you could also ask actually the question, how does, what happens with my excited states? Okay, so how do excited, if I'm not interested in the ground state, but somehow, where somehow would the excited states lie in that kind of thing? And what you see is that indeed if you have a gapped system, somehow the distance of your excited states, the marginals of your excited states versus somehow the ground states, somehow this distance, the distance between these points of excited states versus the ground state, they will scale like 1 over n, actually like the gap of your system, gap divided by n for a gapped system, but for a critical system, somehow these excited states would lie much, much closer to it. Okay, namely they would scale like typically like gap over n squared. Okay, and that's by looking at kind of marginals of excited states, you would and you would also kind of see how, as a function of n, you would see somehow basically where the quantum phase transitions are, or where somehow the system becomes critical, where the gap becomes 0, and so further. Okay, let's see what else can I say about. But anyway, so the real, if there's one message somehow that I would like to convey is indeed somehow that it's this competition between maximal local correlations, okay, because you want to extremize that expectation values. These are, you want to have maximal local correlations, but at somehow just keeping the symmetry. And these kind of two things make that this singlet would have maximal local correlation, but it's not the marginal of a reduced density matrix. That's actually why the ground state of that thing is not, has the marginal not here, but there. And that would be kind of the antiferromagnet. So this is actually the introduction that I wanted to give, but it's apparently, well, anyway, I only have 2 pages, but.
I can ask you a quick question.
Yes?
So you gave us intuition about the bulk being separable states and the facets to the right. Is there any physical picture for when you take the limit and you get those flat planes on the left? What do they correspond to?
Which flat planes? These ones?
No, the white chalk.
This one?
I meant, yeah.
Well, this is just the convex cone of all possible separable states.
I know, but you gave us physical intuition about what the other facets meant, and inside was separable. Is there anything special about those guys? Does that correspond?
Well, I think these would correspond. No. These would exactly be somehow these would be the mean field solutions for the antiferromagnet. So take the antiferromagnet and try to find the best mean field solution. You would get this.
And the existence of those, the purple chalk, the flat parts in the curve.
Yes.
The fact that it becomes, I guess you say it gets kinky, right? It's not C1. That's why you can jump.
Yes.
Jump. So is this has been proved? There's numerical observation?
This is actually numerical observation. Because in 2 dimensions you can only do numerics, but there's pretty good numerics for doing this because this is like a system that doesn't have a sign problem and you can do Monte Carlo and whatever. So this is but this is numerical at the end. This is no. So the blue curve is actually analytical, but these kind of things are numerical. But it's to give somehow a flavor. So the other kind of thing that is very relevant is that indeed you see that if you increase the dimension of your system, okay, so it means if you go from 1 to 2 and so further dimensions, that actually this convex set shrinks, and actually shrinks quite a lot. Okay, there's a big difference between this blue kind of convex set and this purple convex set. And you would go to 3 dimensions, you're even much closer to that diamond. That's actually why simulating quantum systems is harder for lower dimensions than for higher dimensions. Okay, like for 3-dimensional systems, you're already very, very close to that kind of to that separable kind of cone, and therefore somehow entanglement doesn't play a very important role. Okay, so the higher the dimension of your system, the less important entanglement becomes. And that's indeed somehow the folklore kind of result that people already kind of know a long time, that indeed somehow the higher dimensions, if in infinite dimensions, a kind of mean field theory becomes exact, has exactly to do with this shrinking of these convex sets. Okay, so but in the rest of this talk, I think I have like 2 minutes left. I would like to argue somehow how these kind of states that are translation invariant look like that correspond to these extreme points, okay? Because that's actually has been the research that has been extremely active in the last years and that we have been trying to do. Okay, unless there's some kind of more questions about this simple picture, but anyway, so this is like so this is just for that one model, but I think somehow this picture, somehow the same thing should be true for any possible model. Okay, so you have kind of a model of some parameters and you would like to see how the ground state changed. Well, this is actually a pure marginal problem. So characterizing this convex set is of course equivalent to finding ground states of Hamiltonians. This is exactly what actually Maribeth also showed in this picture. So to kind of connect to the talk that we heard yesterday about the two particle reduced density matrices used with these semi-definite conditions. What these semi-definite conditions will give are actually kind of conditions outside of that convex set. So what they will say is that somehow the energy has to be underneath somehow this plane, or it must be underneath that kind of thing. Okay, or well, probably it's much closer in practice, but somehow still what you get these kind of outside faces, and somehow this is exactly what these n-representable kind of conditions give you. They give you kind of, they say that actually the reduced density matrices have to lie under these planes, and these are exactly the semi-definite conditions that we heard about, T1, T2 conditions. This would be the analogs of this. So these are things outside of the convex cone, but actually the approach that that Maribeth also raised, somehow, namely the variational approach, is trying to kind of approximate that convex set from within. Okay, you would like to parameterize states that are translation invariant and live in that kind of cone, because they're translation invariant. Of course, they have to be inside, and you want to kind of find what states do I need, such that somehow they represent pretty well somehow somehow they get very close to the exact. Somehow they approximate somehow very well somehow from the inside that convex set. Okay, and for this what we need is, like I said, we need a method for constructing quantum states that have two properties. They have very strong local correlations, okay, because you want to maximize or minimize the energy, but they must be translation invariant. And in general, this is very hard to do, but there's something that's called matrix product states. Also kind of was used in mathematical physics before under the name of finitely correlated states. And is actually very much inspired by work that Affleck, Kennedy, Leap, and Tazaki did. This is called an AKLT model, where they kind of found one particular example of such a state. And so how do you construct states that kind of marry these two, or kind of merge these two properties? Somehow it is by effectively using the idea that is very kind of used a lot in physics, is that these spins that we talk about, like this spin 1/2s, are actually something like effective degrees of freedom of some much larger underlying Hilbert space. So what you say is that actually my spin 1/2 system is like the low energy physics of some kind of there's more degrees of freedom underlying this. Okay, so we'll kind of, it's like the neutron, actually the neutron, if you're interested in low energy physics, you're not interested somehow in the quarks in the neutron. Okay, but nevertheless, in principle, there's still some underlying degrees of freedom there. And that's what we will do. We will represent actually these spin 1/2s by some other objects that are much higher dimensional. And we say actually that that my physical spin kind of corresponds to a subspace of that space spanned by these underlying degrees of freedom. And what I will do then is take these underlying degrees of freedom and entangle them with my kind of neighbors. Okay, so I think you will understand somehow the picture. So what you do, because we want to kind of construct translation invariant states that have lots of correlations, local correlations. So what we do is take two particles that are maximally entangled. So there's lots of entanglement between these two particles. And there's lots of entanglement between these two particles, but there's no entanglement at all between these two. Okay, because that's clear that somehow, if somehow we would have full access to that space, that would exactly kind of give rise to these singlets that we wanted. Okay, we wanted to have singlets. Well, we say actually these are kind of singlets. But the problem is, of course, that there's a mismatch in dimension. Okay, that if this is a singlet and this is a singlet, then this is like a 4-dimensional Hilbert space, and actually what we want is a 2-dimensional Hilbert space. But that's not a problem. Then we just put a projector here. We put somehow a projector that projects this 4-dimensional Hilbert space to a 2-dimensional Hilbert space, and that obviously gives you a way of systematically constructing states that are translation invariant, but still will live in the right dimension and have very strong correlations, because it's clear that somehow this correlation between these two is mediated by this kind of entangled state. So these are like singlets, and they are kind of connected to each other. Somehow these projectors make actually that you get that you induce a correlation length that somehow everything gets entangled with each other. So it's a very non-trivial kind of operation. This is certainly not a physical operation, but that's at the end the picture that we have. Okay, and this is exactly the game that we have been trying, that we have been playing. So what happens in 2 dimensions, for example, where you can exactly kind of do the same thing. No? What you say is, I have actually also very strong, because I need correlations between these two neighbors. I need strong correlations. Well, you just make more additional virtual particles, okay, and just kind of project this. If this is like, if this would be kind of qubits, then this is a 16-dimensional Hilbert space. Well, you put a linear, you project this 16-dimensional Hilbert space to a 2-dimensional Hilbert space, and you kind of fill your whole plane by putting all these projectors everywhere. Okay, and this is exactly kind of, these states are exactly kind of the states that match that intuition, that they kind of have both properties. They are translation invariant by construction because you put the same projector everywhere, but nevertheless they have very strong correlations. So what I really wanted to talk about is actually the entanglement properties of these states, namely the reduced density matrices, because for these kind of states you can kind of exactly characterize all these reduced density matrices, and especially in 2 dimensions there's a very rich kind of variety of phenomena that arise, that somehow emerge out of this. Namely, somehow there's this kind of notions like edge states. For the physicists in the audience, you probably have heard of edge states. Well, somehow what happens is that actually by doing this construction, it happens that all the physics lives in this virtual particle. So what you want to do is, instead of working with the physics in your physical Hilbert space, you would actually like to describe all the physics in this virtual Hilbert space. That is much easier. Okay, that is actually so you will be able to kind of map somehow by finding some isometry that maps these virtual degrees of freedom to the physical ones. And doing the physics in the virtual degrees of freedom leads actually to a much more concise and much more efficient way of dealing with these things. Okay, and at the end, somehow all the entanglement is kind of the entanglement in our system will be related to somehow the mixedness of your reduced density matrices. But I really don't have time to talk about these things, so I think I have to stop. Thanks.
Any questions, Frank?
Yes.
If you just keep it, let's say, one dimension and take a model like an XY model where you have some quantum phase transition varying external fields, say, is there any way to spot the transition just at some special point of the curve?
Well, yeah. So there's some, so exactly at that point, somehow there's some kind of non-analyticity kind of going on here. But I'm actually not, because I've never kind of written down the exact kind of analytical formula for that. I have not checked that, but that would be a very interesting question. There must be something happening at the phase transition.
Yeah.
There must be something non-analytic going on here.
Right.
But it's not. This is well, we have not investigated that. But it's indeed a very interesting. It's a very interesting kind of question. How to see basically quantum phase transitions. Okay, so certainly by doing finite size scaling, by kind of trying to see how fast does kind of by drawing these plots for finite n, what you will see is that in the gapped phases, somehow this inner convex set will converge exponentially fast to the right one as a function of n. But except at the critical points. At the critical point, somehow this convergence will be much slower. Will be kind of like 1 over n. Okay, and that's how you could. That's certainly a way where you could spot where the phase transition is. Namely, somehow by doing finite size scaling, how fast do you converge to this? I will see that at the phase transition it's much slower. Yeah. Yes.
Good question. Is there a way to see that as you take dimension to infinity, that entanglement doesn't play a role using this picture? That mean field theory becomes exact and so forth. You can project down on.
Well, not really actually. This is indeed not clear. There would still be lots and lots of entanglement here, no?
Yeah.
Because it's no, that's actually not easy to see. But at the end, it boils down to what. Well, in some sense, it's clear that this reduced. If you have the symmetry in that thing in high dimensions, that the reduced density matrix between these two sides will be equal to that one and so further. And then, because of this monogamy properties, we know that it will be very close to a separable state. So that means that actually there's no need for these kind of links. You could as well do it with having no bond dimension at all. So mean field theory would correspond actually to just having no entanglement at all between nearest neighbors. That's what mean field theory is.
Any other final questions?
Am I right that you found 4 phase transitions in that model, according to your picture?
4. Well, yeah, but somehow this is not fair. This is like the fact that you can map this is just some symmetry of the system, and at the end there's
This is just phase transition from ferromagnetism to anti-ferromagnetism.
Yeah, this you can certainly. So first order phase transitions are very easy to spot in that picture because they correspond to the phases.
Exactly. Yeah. And do you also have such pictures for larger spins, like spin 1?
Yes. Well, if you can solve that, if you can find the energy as a function of some parameter, then you can always draw these pictures. And I don't understand. So these pictures. So actually the talk that I gave here is some kind of work that I did in 2005, and in some sense nobody has followed this up and has tried to kind of make these pictures for other kind of models. And nevertheless, I think it's a very interesting problem. Actually, I have tried to give this problem to my students, and they all refuse to kind of look at this because they don't understand how to do it. But yeah.
Did you publish this somewhere?
Yes, this picture was published. Yes, in a paper actually on matrix product states in 2005.
Okay, we can have one more question before the break.
So what happens if you lift this problem from the two body, the two first neighbor, qubit to say 4 qubits? Do you gain something more? Because you can.
So your question is, what is the complex set of reduced density matrices of translation invariant states, the 4-body reduced density matrix?
Yeah, because in this case you can compute everything. You have the energy and whatever. Do you gain something?
But it's yeah, but it becomes, of course, you have much more parameters there. Yeah. You have much more parameters and it becomes a high-dimensional object, and I don't know. Well, I don't know. Of course, you should see everything. Everything should be in that kind of picture, but I don't. Well, yeah, we have not tried.
Okay, so let's thank Frank again and have some coffee.